Power Series, Video 1. Here's what a power series looks like. There's definitely a series, and there's definitely a power. Take a closer look. Unlike a regular series that we have studied, we're now in power series having the index begin at 0. The CNs, those are sitting in front of x's. The CNs are the nth coefficients. The x's are real number variables. We're eventually going to want to look at the power series as a function, and functions typically take x's as input. A is the center. Nice. In studying series in general, the big question is usually convergence. Does it converge? And that used to be focusing on, well, what are the terms of the sequence where the terms are just fixed? Now that we're allowing for an x to be part of the terms of the sequence, the question is going to be, for what x's does the power series converge? So, for the rest of the video, we're going to do a proof of this theorem. And in the theorem, there will be 3 statements, and only one of the 3, exactly one of the 3, will hold true about the convergence of a power series. Good? First one, we can plug in x equals a. You'd then have zeros, and you can sum up zeros. And then that's the only place that you can plug in an x at a. That's the first case. Second case is that you can plug in any number that you like, and this will be a convergent series. A trivial example would be where all the CNs, the coefficients, are 0. Any number x would work. The third case is something in between, where you know you can plug in x equals a, but you can only move away from a an amount capital R, and if you move away more than that, then the series diverges. Note that at the endpoints, exactly capital R away from the center, you have to check for convergence or divergence. Good? So, the proof. To set up the proof, we're going to change variables. Instead of taking the center at A, we'll suppose that the center is at 0. And then, to consider the 3 cases, we're going to rely on this fact. So first, let's prove this fact. So here's the statement of the fact. So if we have a non-zero, i.e. something not the center, and this series given by the CNs is able to converge, where you take the coefficients and place them on d raised to the power n, then for all values which are closer to the center than d is, that the series that the y's define will also converge. Good. So here's our assumption. We have a non-zero d, and we're having that the series it defines converges. That means that these terms must go to 0. That's the divergence test. And if they're going to 0, then they're getting close to 0. So after some point, all of the terms must be within 1 of 0. Nice. Next, we're going to use this fact to find control of the sequence in the series we want to converge. So if we take y to the n and leave it as a numerator, and then multiply, interject a 1 in here in the form of d to the n over d to the n, and then estimate away the cn d to the n with 1, then we can see that we have our guys that we want to make a statement about convergence for their series being controlled by this quantity. So what can we do with this quantity? And note that it's being raised to the power n. Well, we can take those quantities in the numerator, make them smaller than the denominator. Then this ratio would then be less than 1, meaning that this quantity, this series, is a geometric which will converge because the common ratio is less than 1. And by this inequality, we can use the comparison test to gain that our series converges, and note that it converges absolutely. Converges absolutely. Nice. That finishes proof of the fact. Fantastic. We'll go back to the proof of the theorem. So now that we have the fact, let's start the proof, and we'll begin by saying that S is the set of all values such that the series they define converges. And we'll consider cases. The first case is that the only place that we can plug in is the center. And that's exactly corresponding with case A in the statement of the theorem. Another case would be letting the set of all y's that converge be the entire number line. And that is case B of the statement of the theorem. So case 3 is going to be the in-between case, not just the center and not the entire number line. All right, so we're not case 1, we're not case 2, so we make that statement explicit. Let's focus outside of S. Because we're not the entire number line, we can find a non-zero, something not the center, which is not in S. Therefore, the series that it defines will diverge because that y tilde is not in S. By the fact, we're then able to conclude that all values that are further away from the center than y tilde is will also diverge. That means that there is a bound on S. You have the center, and then S has points that only go a certain distance away from the center. By being a bounded set, it's a property of the property called the least upper bound property that S will have an upper bound. Call that R. And then because we know that there are points other than the center in S, R is going to be positive. Therefore, everything that is closer to the center than capital R will be in S, meaning that case 3 holds. And that completes the proof. Excellent.